Welcome to Data Science 1, Probability, Standard Normal Distribution. Things we need to remember: sample space, random variable, cumulative distribution function, probability density function, and the normal distribution. If you haven't watched the video on the normal distribution, this might seem a little bit confusing, so you might want to back up and watch that first. All right, so standard normal distribution comes from this idea of standardization. Okay, so when probability was first being developed, computers were not available and as readily accessible as they are right now. Right now, you can pull one out of your pocket, and sure enough, you can type things into Google and it'll calculate things for you. However, pre-calculated tables at that time were what people used. You may have actually seen some of these. There used to be trigonometric tables, logarithmic tables, and of course, what I'm talking about now are probability tables. And the goal is to use standardized tables so that you could just use one table instead of having to do a whole bunch of possible tables. Okay, and often these tables had in them what were, I would say, difficult calculations. Okay, in the sense of it took a lot of time and effort to build these tables so that one could use them, and that's why they wanted this idea of standardization. And the legacy is present all over the fields as engineering, and it'll come up when dealing with statistical procedures. Okay, so how do we get to a standard normal distribution? Well, a standard normal distribution is just a normal distribution with a mean of 0 and a standard deviation or variance of 1. Okay, the standard normal distribution, if we suppose we have a normal distribution and we want to get to a standard normal distribution, we would use this formula here: z equals x minus mu over sigma. And notice I put a z here. Usually when you're talking about a standard normal, you always see a z associated with it. And if we have a standard normal distribution, we have a number from it, and we want to send it back to the original space that it was talking about in its normal distribution, then we would use x equals mu plus z times sigma. It's pretty easy to do. Now, what I'm going to point out here is you may or may not have gone through this module yet, but you'll see that when you do test statistics, they tend to look something like this. Okay, there'll be a divide sign, there'll be a subtraction in it someplace, and there'll usually be a z on the end, or possibly a t, but we'll get to t later. And then if you're doing a confidence interval, you'll see something that looks like something mu plus z sigma. So these are sort of the basics of where those come from. All right, so what do people do? If they needed the CDF, they would jump in and go to a table, and this table was found at the University of Arizona. Thank you very much. I didn't want to make my own right now. But here you can see you would find the z value, and you would say z0, got to learn how to read it. And then that's just too bothersome. Let's not even learn how to read it. We'll skip it, and we're going to let the computer do it for us. Why not? They're everywhere. However, you do need to know about this distribution. Just because the computer will do it, this distribution keeps showing up again and again and again, the standard normal distribution, and it will show up again in the central limit theorem later, and it comes around on its own. We don't actually try to get it to happen. It does happen. All right, so let's look at some basic properties and learn how to play with the standard normal distribution and learn about what it can tell us. So number one, it's bell-shaped and symmetric. Bingo. Okay, it has inflection points. The mean is at 0. Inflection points, if you know what those are, it goes from being cupped up to cupped down. So that's where the inflection point is at -1 and 1. And we can see that if we go 2 standard deviations out, from -2 to 2, after about here, notice how low the likelihood goes. The density is not very high in this region, meaning that the values outside there become less and less likely. Okay, so the probability, if I'm going to be between -1 and 1, about 68% of the probability is between -1 and 1, which means, well, you have to remember these probability distributions represent your population. So about 68% of the population would be between between -1 and 1. If we go 2 standard deviations out, we get to 95.45 of the probability. 0.9545 is the probability you're between -2 and 2. And if we go out 3 standard deviations, then we know that 99.73% of the probability is going to be between -3 and 3. And this forms what's called the 64-95-99 rule. And I've seen students learn this, and they're like, I don't have any idea what you're talking about with this. The whole point of this thing is it gives you intuition about what may or may not be a reasonable value. Okay? And you can do these calculations rather quick in your head or easily on a calculator. So let's look at a couple examples of this. Suppose somebody told you that for some experiment the mean was 10 and the standard deviation was 2. And they said they observed a value of 13 and claimed that that was a very high number for this sort of experiment. Well, what do? Well, you do a quick calculation. Z equals 13 minus 10 divided by 2 is 3 halves, which is 1.5. And we know that values between minus 2 and 2 are very common. So I would just tell them 13 really isn't that high of a value. I just tell them. And notice that I just use intuition and just a really simple calculation. Very simple calculation. You could go the other direction. Somebody told you the mean was 300 and the sigma was 25, and they wanted to know what values would be suspiciously high. Well, we know that almost all the probability, 99.73% of it, is going to be between minus 3 and 3. So anything that's beyond minus 3 and 3 on the standard normal is going to be really rare. So we just flip it back over into the units that they have. Well, we'd say, okay, mu plus z sigma. Mu is 300. We pick 3 because we know anything outside of that's going to be odd, times the standard deviation equals 375. And so any values larger than 375 we would deem suspiciously large. All right, so I didn't actually show you the PDF, but here it is. It's just the same as the normal, where I plug in a 0 for the mu and a 1 for the sigma, and they go away. There's no closed form. We're going to use a computer. The mean is 0 and the variance is 1, and we can get some intuition from this. And that's the big thing I want you to take away from this, is we get intuition, and it gives us the ability to work with other distributions later. So the standard normal distribution is very, very important to help us build other distributions later, helps us build test statistics and all sorts of things. So you'll see these in the future. So when you think about the standard normal, just because the computer will do it now, doesn't mean it's not important. It means that it's kind of a building block that you won't interact with a lot, but unless you're actually a statistician and you want to go through all the math. But it is very, very important hiding in the background. All right, so we're going to move on to the next video, and I'll see you there.